Okay, thank you. My name is Catalina Giraldo-Soto. I come from the University of Basque Country, and I will present the summer uncertainty estimation of indoor-outdoor air temperature collected from a 3D monitoring and control system installed in a tertiary building. So this is the table contents with the follow. So the heat transfer coefficient is a potential key performance indicator for the new energy performance certification of buildings. And for the reason we need to improve the technology, the monitoring and control systems to be integrated to the building automation system. And it's really important to have an experimental test for reliable HTC estimations. So to have reliable HTC estimations, it's necessary to optimize the monitoring and control system. And what is these optimizations? We need to know what is the number of sensors, the best sensor layout, and the best technology, trying to reduce the uncertainty of the measurements. So also it's possible estimate the HTC uncertainty of the HTC from the physical variables that is collected from some sensors. In the case of the occupant building, we have this energy balance, and we have the other occupant buildings used for the computing index. So all these variables, physical variables, are intensive variables, and all have systematic errors, but only the measurements associated with random errors at the occupancy gains. In the case of the occupant building, the heat fluxes sensors, the indoor and outdoor temperature measurements, and the solar radiation gains. I will present the measurement uncertainty of the indoor-outdoor air temperature. And we have estimated the systematic error not only of the sensor, but it includes the sensor plus the monitoring control systems equipment. So you can find here the two papers that we have published in building environments and the building physics and the methodology. So we have implemented two uncertainty tests, the sensor together test and the random test. The difference between them is in here, all sensors are together with the same wire that we will do the monitoring in the building. And we included the systematic error, not only the sensor, but it included also the monitoring control system equipment uncertainty. And the other side, we have the other uncertainty test is the random sensor test, where you install all the sensors randomly in the thermal zone that we want to study. When we have the both tests, we have two different uncertainty. I call it to this uncertainty measurement sensor uncertainty. In the case of temperatures, is temperature sensor uncertainty, and the random test that estimate the overall uncertainty that include the systematic and random uncertainty source, and we call it measurement uncertainty. Or in the case of the temperature, for example, is temperature uncertainty. When we have estimated this both uncertainty, we can implement uncertainty decoupling method when we can estimate the uncertainty only associated with the random errors. So we call it to this uncertainty measurement spatial uncertainty. In the case of temperature, is temperature spatial uncertainty. So I will start to explain how I did this analysis data for the measurement uncertainty and measurement sensor uncertainty. So it's based on the count methodology. So we have intensive variables. So we have the uncertainty type A, and we need to have independent variables. Usually the sample, the people use the temperature as the sample. In our case, our sample are the instant of time, and we need to guarantee the independent variables. So for this reason, we transform the raw data in temperature differential. So we estimate the average temperature of each instant of time, and we did relative estimations with center data with respect or true real value. What is the true real value in your case? The average temperature or the real temperature that we have in the thermal zone. And the hypothesis of this real value for us is the average temperature that we have estimated with all the sensors installed randomly in the thermal zone. When we have this, we can guarantee this requirement for the uncertainty step up, and we do the estimation of the statistical parameters to obtain the expanded uncertainty. When we have all the uncertainties due to the overall uncertainty and also the sensor uncertainty due to systematic error, we can implement the decoupling uncertainty decoupling method. How? Using through the variables of the both kind of uncertainty, we can implement the temperatures, we can estimate the temperature spatial uncertainty, and also we can see what is the weight of each systematic error and the random error. So our experimental test. So this test was carried out in tertiary building in Bilbao. It's a retrofitted building. We have 4 offices. We have also 2 kinds of sensors. The 800 is for indoor air temperature, and the 71 is for the outdoor air temperature. So in the case of indoor air temperature, we conducted the sensor together test with all sensors, with all the equipment and hardware and software is included here to estimate the uncertainty associated to systematic error, and the random error and the random sensor test is with the sensor randomly installed around the difference of typology studied. So here we have the 4 office typology with different orientations, and this is an example and pictures of this test. In the case of the outdoor air temperature, we also we need to put all sensors together, and also the random sensor test. The sensor was installed in different facets of the building. This is pictures about this, and the data analysis results. So I will show you first the results of the uncertainty with the based on the uncertainty test. I will see also the results of the uncertainty decoupling method. So we have here the results. We have here that the temperature sensor uncertainty of the manufacturing is 0.13 Celsius degree, but only of the sensor. Even so, when we do the sensor together test, we can find that the temperature sensor uncertainty, so the uncertainty due to systematic error of sensor plus monitoring control system, is around the 0.24 Celsius degree. So the overall uncertainty, so that result comes from this random sensor test, is different, depend of the facade where the office typology is. And so, for example, office typology 1, office typology 2 has only northern facade, and the office typology 3 is in the southern facade. And
2 minutes.
Okay, and finally, for the office typology 4 that have a different orientations, have these uncertainty estimations. The random errors, the uncertainty associated to random errors is this value, and here we have the random weight and the systematic weight when the spatial ratio is greater than the systematic weight. This is the difference, pictures the different manufacturing accuracy and the sensor temperature accuracy that we have obtained experimentally. And here, in this case, we can note how the overall uncertainty is greater than the temperature sensor uncertainty. Oh, with this uncertainty, we can find the rank of the true value where the indoor air temperature of each office typology can live with a confidence interval of 95%. Similar for the outdoor temperature, we expect to have the sensor test when we finish the experimental test in tertiary building. Even so, we did this estimation from the manufacturing accuracy. Here we have the random sensor test, the uncertainty associated in different periods. We have the wall period with solar radiation gains and without solar radiation gains, periods only with solar radiation gains and periods without solar radiation gains. We have here the temperature spatial uncertainty that is too close to uncertainty, temperature uncertainty, and we can see the weight of the random uncertainty source. So we can see the difference between the overall uncertainty and the spatial uncertainty. And we can estimate also the true value where the outdoor air temperature can live. And the main conclusion is the most part of the research of the works estimate take the manufacturer accuracy sensor as the overall uncertainty of the indoor air temperature and the outdoor air temperature. So it's important to note that the result of uncertainty of the indoor air temperature measurements show the importance to estimate the uncertainty of the raised variable of the HTC. And it's important to know that the weight of uncertainty, the sensor weight and the random weights allows to know the degree importance of all the temperatures spatial uncertainty. And finally, the outdoor air temperature give us the same results. Main conclusion is they only consider the sensor manufacturing accuracy of the overall uncertainty, least stronger underestimate the overall uncertainty. And for the work period is this value 2.22. And when we do the sub-periods with solar radiation with the solar radiation gains, we have different values, and the main conclusion, the solar radiation incidence is one of the main random uncertainty source. So it's important to estimate the HTC on the included days to reduce the uncertainty estimations. And also it's important not only consider the manufacturing accuracy and the overall uncertainty of the outdoor air temperatures. Thank you.
Who's next? Francis?
Slides over there.
Yeah, it should be on there.